Hey there and welcome to the Big Apple School podcast. My name is Sam.
And this is Mike.
And today we're asking what's the crack about construction. So we're going to ask what it is, who decides what to build. I mean, where do those buildings come from that we see? So we're going to ask questions to kind of raise awareness about bridges, culverts, buildings. Where do they come from? How many have we been involved with in our lives? What kind of different types of construction there are. I'm going to share a little bit of knowledge about that. Nothing too extreme, nothing too technical. We'll talk about forces, a little bit maybe about materials, about the problems with buildings and bridges. We will ask who is better, an architect or an engineer, and talk maybe a little bit about our favorite structures, bridges or buildings or whatever. So all good? All good in the hood?
Yeah, but I got a question for you, sir. What
really?
Actually, when we say construction, what does that actually mean? And who gets to decide what to build and what to do with it?
Okay, so construction is, of course, a big industry. There are multifaceted.
That's right.
Mostly multifaceted.
Yeah, it's so confusing.
So you've got builders, you've got civil engineers, you've got roads that need to be constructed, and they aren't just thrown down. It isn't just one layer. There are multiple layers to them. You've got roads, you've got buildings, and of course there are buildings that are purely for living in, but there are also buildings for different purposes, for governments, for government buildings. There are bridges which have to be thought of carefully. There are lots of things that have to be thought of, and there are lots of different elements in that. You've electrical stuff, mechanical stuff, all kinds of weird and wonderful stuff goes into.
I was in Seoul just before arriving here to Novosibirsk, and they've built an airport on a man-made island, and they've decided to interconnect it to Seoul with a huge bridge.
Yeah.
Now, I've always been a big fan of long bridges. I've always wondered the engineering that goes into those things, how to make it stable. What goes into building a bridge?
Right. So, what I worked way back when, I feel like I worked in a civil engineering office, and we were involved in roads and bridges and work for the government. And what I maybe didn't realize prior to that was that it's a team. It's not only civil engineers, and there's a lot of it is civil engineers, and they're figuring out the calculations and what problems it might have and what best configurations, and balancing cost and benefit on all kinds of thoughts. I mean, years and years of work going into it, but it's not just civil engineers, but they're supported by technicians. I was a technician on AutoCAD, an AutoCAD manager as well. And they're supported by those guys. They're supervised. There's finance. I mean, who finances it? So it's a big decision, and a lot of years of work go into that. And I'm sure that there were quite a few years involved in that bridge that you're speaking. Incheon Bridge, I think it's called.
Incheon Bridge, yes, correct.
And I've looked into it a little bit because you've spoke to me about this.
Yeah, that's huge.
And it's not just one bridge.
Yeah.
I mean, you can look at it. There's several different structures involved, and there are different elements to it. And there's the bigger parts, but also there's the road leading up to it.
Oh yes.
And it would have been, of course, done in stages and designed in stages, and the route would have been planned. All sorts of things that a normal person wouldn't realize automatically goes into this.
Yeah.
This whole stuff. So it's very. I don't want to scare anyone. It's very technical, but at the same time, it's not done by just one person. So it's not like one Einstein kind of person sitting there. I know what this will be. I know what we'll do here. Well, it's a group. It's a team effort.
What really surprised me about that Incheon Bridge was they've actually blocked the sea. That part used to be where the sea used to pass. Okay. And they blocked that out. So you actually see fields of mud, essentially. And you see a little bit of water coming in, but it's nothing to threaten the bridge. So my guess is that movement of the water and the currents really threaten the integrity of a bridge.
Absolutely. I'd like to talk about that because that is one of the weaknesses of bridges, but we'll maybe talk about that a little bit later.
No worries. But Sydney obviously has a huge bridge. Yeah, basically we call it the Sydney Harbour Bridge.
Yeah.
And it was constructed well over 100 years ago. Yeah, and when it was built, a few people died building it. Yeah, and it took many years to do that. It was done in sections, as you say, and when it was built, it was considered a technological marvel. Yeah. And I've heard some engineers say that it cannot be replicated today. Right? Is that true? Surely.
Well, not being super familiar with it, I think that it would depend on the materials that were used, because maybe some of the methods, sometimes some of the methods and the skills involved are lost.
Really?
Yeah, especially like some of the, much older style, or there was some skill involved, or maybe, if it's a special kind of metal, like rather than what we tend to use nowadays is iron for different constructions. Iron and, of course, other materials, reinforced concrete is very popular, and steel is popular.
Yes.
Whereas in the past, it was maybe cast iron or special, different types of iron, and those materials are not used so much now, or not used at all maybe now.
Actually, sorry to interrupt, but Sydney Harbour Bridge, if you look at it from the surface, it does look like cast iron. It does not actually look like steel.
Right.
So maybe they reinforced it over the years with more steel beams, but overall, it's got this black cast iron look to it.
Yeah, it's quite possible. I've seen the picture, but to be honest, I haven't researched it. So I would suspect it could be because it's materials that involved some skill in creating that it's fallen out of fashion or use, if you like. It's not like it's not to say that the shape couldn't be replicated and the form and the how it functions couldn't be replicated, but maybe the actual use of the materials is not. It's different now.
It's different now. Okay.
Yeah.
Okay, but I just find that the bridges are really, really remarkable, and bridges aren't the only thing that's remarkable for me. I love architecture, and especially I find so much great architecture in Novosibirsk. A lot of people don't like it, the locals, but I love them. I love seeing it. Have you been to, like the buildings? What's your thoughts on the buildings? I really love the old Soviet-style building construction, but I don't know about you. What's your opinion on buildings?
I appreciate the Novosibirsk Ballet Theater building, Novat, it's called. And I love the dome. It's great inside, but I like it outside. It's quite imposing, nice big structure, a lovely dome. And for me, that kind of form with curves and strong lines and everything it's fantastic. Even though I worked in civil engineering, so it's not. Most of the time, civil engineering is not concerned with buildings, although there is that side of it too. It's not. A lot of civil engineers not buildings, although it can be. So I don't know, or I haven't had a lot of experience with architecture per se, but I appreciate good architecture.
I see.
Yeah.
And, every day I go into some building and I see things I've never seen where I grew up. It's almost like sometimes it's in a different world. What about you? Any interesting buildings you've been to there?
So what I would point out is, or what I want to say is to people, is that bridges and culverts are everywhere, and architecture is everywhere too. And I think that we are kind of blinded by, especially if you're living in a big city or a town, or even when you're going through the countryside, you will cross a bridge or a culvert, which might be buried or partly buried. Or you will walk past a building and you won't notice it because there's just so much happening. And like back when I used to go and inspect bridges, I used to go out onto the road, and you would literally drive over 2, 3, 4, 5 culverts or bridges without really thinking about it.
I see.
And unless you're actually conscious of it, you'll miss the architecture, you'll miss the bridge, you'll miss the culvert. And maybe you should take a little time to appreciate it.
Well, I mean, architecture being art, and art has to be appreciated in detail. Art is all about detail. If you just have a look at it with one glimpse, you're never going to be able to appreciate that art. That's what I believe.
I think so. But then on the flip side, I mean, beauty is in the eye of the beholder, but there are bridges, there are buildings that are function rather than beauty.
That's true. And that's where architecture is a little bit different from the other arts, because it serves a practical function.
As well as an aesthetic practical.
Yeah, as well as an aesthetic beauty, right? But I always wondered, like, what kind of construction, what types are there for these bridges and buildings, and how they actually work in sort of engineering principle,
Right. So this is where I hope I can educate you as best I can.
Do.
So I'll look at it a little bit more from bridge point of view, but we can relate it to architecture too. So in bridges, there is a wonderful thing called an arch bridge. And it takes the form of a circle, if you like, although it's three-dimensional, of course. And what it does is when pressure is pressed down on one point, that one point starts to press into the other points. And if you like, it supports each other. It's a wonderful natural shape, this arch, that when you press it, it all kind of pushes back at you. And domes as well. If you're thinking more about architecture, a dome, it's a kind of self-supporting, because one piece of it, if you look at it, if you just try to visualize one piece is pushing down on all the other pieces. And they are in turn kind of pushing back, if you like. So it's a kind of self-supporting structure with the forces coming down, things pressing down on it, even just gravity. It's kind of holding its own, if you like, and each of the parts are working together to hold it up.
I think the Romans were one of the first people to use that principle.
It's about 3,000 years old, maybe more.
I think so. I think they were originally taught by people called the Etruscans, and I think they used. I mean, domes is one of them. The arches, one of them. I think they used something called a keystone technology.
Keystone is the top middle part.
That's right. Yes.
Right. And once you have that in place, as I say, it's pushing down on both sides of the arch, and they're in turn like kind of pushing back. So it's a self-supporting kind of system.
So what happens if you don't put a keystone?
If you take a keystone, it doesn't work.
It actually collapses under its own weight.
Without the keystone, it doesn't function.
It actually doesn't stand up.
If you take one piece out of that arch, it'll start to collapse. It'll start to fail.
I see. So this is where it can be quite fragile.
Well, yes, it can be.
So if one key,
it could be.
One key structure is damaged or whatever, it can actually collapse the whole thing.
So what I did and what you need to do is inspect them.
I've seen it. I've seen that. I have seen it at Novosibirsk train station, the big one, the teal-colored one, where there was this guy, young man, with a couple of attendants from the train station, inspecting everything from the door into the grills of the floor. And I was thinking, what is he doing?
Yeah,
and I think that's what he was doing. He was checking the structural integrity of every nook and cranny of that train station.
Because you've got all those little parts. Oh, beams. Okay. So I'm not quite finished yet. So beams running from one support. So maybe it's a pier, maybe it's a wall, something that's supporting. And of course, two things, of course. And you've got a beam running between that. And then, of course, it's quite simple principle. You put something on top of that beam and it'll support it. Nothing drastic about that. But beams, of course, are very, very popular construction. Simple stuff like that. Trusses. Do you know trusses?
Actually, I don't.
Basically, it's triangles. If you want to boil it down, triangles.
Triangles.
Okay. So if you think of shapes, if you want to look at construction from a shape point of view, we've got circles or semicircles. That's your arches.
I see.
And triangles. And they are quite similar in principle in that if you press on one point, the other points kind of push back. And so it's kind of a self-supporting idea. So trusses are essentially triangles. They're often made from steel or cast iron if they're older bridges. And so they kind of support, they're a wonderful shape to support.
I see.
Triangles, and circles.
And bridges are often made of all these shapes in combination.
Not just bridges, but you'll see them in buildings too.
Buildings too, okay, both. Talking about structural integrity, when I was in university learning physics, they showed us what oscillation can actually have effect on bridges, what sort of effect oscillation can have. And they showed this old film clip of a bridge. The winds caught the right oscillation, and basically it started acting what's called torsion force onto the bridge.
Right.
And eventually,
lovely technical.
And eventually, basically the bridge collapsed. It was a big bridge, but it just collapsed. It didn't even seem like a high force wind. It didn't seem like high force winds were affecting it. Yet, with enough frequency and vibration, they were saying that these things can actually. But that's before they figured out certain engineering principles to make it stable. So can you run through a little bit about that? What sort of forces affect bridges and how do we, combat these things?
So there are 4 main ones. Compression, which is basically push. Pushing down or pushing across or pushing together or whatever. So compression is a thing. And tension, which is basically bending, right? If you think of a ruler and you try to bend it, unless it's a very special ruler, it will break eventually. There is torsion, which you mentioned, which is basically twisting. And it can happen for various reasons. It can happen because of wind. It can happen because of some other push from the side or from above or whatever. Shear is another thing, which is basically when you cut down or through a structure. And it's interesting what you say is, I believe it's the Millennium Bridge, is a footbridge in London.
I think that was it.
They built it and they did a very good job in one sense, but they didn't consider, which is probably not something that's often considered or wasn't often considered. They didn't consider the fact that it swayed. And people started to move to the kind of rhythm of this sway. And that had a negative effect on the bridge. And what do you have to think about structures? You have to think about the wear and tear. You have to think about not just these forces like pushing, bending, twisting, cutting, all of these kind of things. Sounds like a Lord of the Rings.
It does,
the ends. But you also have to think of this is happening regularly. This is happening. You have to think about the frequency of this kind of forces as well. Not just how much and how strong it might be, but the fact that it can wear down the bridge.
Is that term in English we use entropy?
And right. So it's the idea. Well, the idea is that you've not just got a truck, or you've not just got people walking on a structure, but you've got maybe multiple trucks or multiple people. I mean, you've got books. Books are very heavy if you're thinking of a library. So it's necessary to think when you're designing, building a structure, to think about think of practically, about what will actually happen throughout its life. What will be the worst effect?
Well, I guess previously water obviously must have a huge force on it. But what are some of the other problems for buildings and bridges?
So what interested me when I started to get into inspecting bridges and learning about how they're built and what negative effects, water, something as simple as water is like a destructive force. And I mean, I guess it's not a super surprise, but the sort of philosophy of that idea, the simplicity of that, just something that we need every day. We need water to drink, to clean, whatever, can have such a destructive force. If you've got a flood, your arch bridge, if it's pushed by a flood and stones are removed, which they can be, then it starts to lose its strength and it starts to collapse. And there are many arch bridges which have stood for years and years and years, decades, maybe hundreds of years, but a flood has come and taken parts out of it and it's collapsed.
I think I've seen a video of that. I think there was in Bali about 10 years ago or so, there was a big flood. And you actually see tourists filming with the videos and it just comes in and just knocks everything. And it's not even a huge flood. It's actually low level. But it just swept through the bridge, the village, and it just wiped it clean.
And another thing is that water can carry salt and other harmful chemicals inside a structure. It can be a building, it can be a bridge, and it can carry it inside it. And often in bridges and structures, you have steel, either inside or outside, and it will carry it in, and of course it'll start to rust either inside or outside a bridge or a structure, and that of course rust is generally thought as bad, and it is bad.
It is bad.
So water carries that too, and it might be dripping through cracks. It might be a very slow process. It could be also water plus cold plus a cycle of wet and dry, or cold and hot. So the elements, if you like, it can be freezing as well if you got water that goes into a crack. And when it freezes, it expands. And that's, of course, going to expand that crack. So water alone can destroy a structure if you just leave it alone.
Really?
Water alone will do it.
Is it through the corrosion?
It's not going to happen overnight.
Right.
But if you leave it long enough without maintenance, without any attention, water alone could get into areas, cracks, and any kind of area, and it will destroy a bridge.
Wow.
It has that potential.
Yeah. Wow.
Over time.
Okay, so let's say the San Francisco Golden Gate Bridge, even if there's no current, basically, if you leave it long enough without maintenance, it will just, no matter what the scale of it is. What water, and if it's salt water or seawater or whatever, it gets, especially if you've got a bolt, it'll get into there, and because of the differences, it's not a uniform structure, it's not a uniform shape. Water will start to sit in certain areas, and it will rust. I see.
And that's where rust often affects the most.
I see. What are some of the other forces?
Wind can often, especially if it's a very big, very tall structure, you have to absolutely think of that. If it's a smaller bridge or a smaller building, you don't have to think of it as much. But if you're starting to build big, like your South Korean bridge to the airport, you really have to think about wind.
I see.
What happens at times, interestingly, as well, is if you've got a bridge, especially if it's a low bridge, and it's maybe an older bridge, because generally newer bridges are built that bit taller and it's thought of. But there are quite a lot of arches and lower bridges which are hit by lorries and trucks.
I see.
And so you've got impact to think of.
I see.
For your Korean bridge, they have thought of being hit by ships.
Yes.
They had to think of that.
Yeah, because it's a trading nation. That's right.
Yeah, and they had to, by the way, if you're talking about a big bridge like that, they have to think about a channel to allow ships through. They have to. They must. They have to think about the width. They have to think about the height. And they have also thought about impact. Because a ship, even if you don't assume that a person in charge of ship is sensible, even though 99% of them absolutely are, you assume that it's going to be hit. And you have to think, right, what will happen? What is going to happen to this bridge if it does hit? How can I stop that from happening? Because I don't want my bridge to fall down or my building or whatever.
Well, one of the things I noticed in Sydney Harbour, we always have big cruise ships, these Norwegian cruise ships and whatnot, and they are massive.
Yeah.
I think some of these are like a kilometer long, I think.
Wow.
And basically, they're always docked at Sydney Harbour to take on passengers, because Australians are huge travelers on those cruise ships, right? And basically, and they're always under the Sydney Harbour Bridge. And part of me always thinks, as they go by, as they go under it, I'm thinking, will it hit the bridge? But it never quite hits the bridge, right? There's a safety margin they've always considered.
Yeah.
But a part of me thinks these things are massive. They're as big as oil tankers, some of these things. If they hit Sydney Harbour Bridge,
they hit it would be,
as big as the Sydney Harbour Bridge is, I can tell there's going to be fatalities no matter what.
Well, it should have been thought of. And I assume that it has been thought of in the case of just some of the older bridges. It's because some of the older bridges, life has changed.
I see.
And trucks and lorries have got bigger.
That's right.
Traffic has got bigger. So, but as long as a newer bridge, it will have been thought of how high do we need to make it? And as long as those boats and ships that are going under it don't change, then the bridge will be suitable for it.
I see. And, basically, the question I've always had is, architect.
Yeah.
There's an architect who draws it up. In my knowledge, right? Basically, my common day knowledge is that architect draws up the plans, makes it aesthetically pleasing and functionally viable. But then there's the engineer.
Right.
I don't know what he does. What's the difference and what's the distinction between those two?
Right. So there's a joke among engineers, and maybe it's not very fair, but there's a joke that the architect designs something, draws it up, does a sketch, gives it to the engineer, and after he's picked himself up from the floor, after laughing, he starts to tell the architect what he can actually do, what he can actually give him. And I think it's unfair because that's an engineer joke. That's not an architect joke.
Right.
But basically, it explains what the two are. So an engineer is a practical kind of guy, and he thinks about the calculations, about the forces coming down, and what is needed to push up against those forces.
I see.
How to balance the forces so that a structure stays standing. And he is a very practical person, but unfortunately, and it's not always true, but unfortunately an engineer often doesn't care much about how it looks. And that's not true for every engineer. It's not true for every project. In fact, many projects look fantastic. But often an engineer is compelled to think about the practicalities, about cost, and isn't too concerned about the aesthetics. And that's not to say that it's completely out of his mind, but it's often not the focus and not the priority. And the client who's financing the project will make the decisions on often the client makes the decision on what he wants and how it looks. And so the engineer is more employed to think about, will this work? And to tell the client, like, this is, here are your options, here are some options, and here are the costs associated. And the client often makes the decision. An architect is often focused more on the aesthetics. And that's not to say that an architect is not practical. It's not to say that he can't do calculations, but often the two will work together, to be honest. And the architect will help more with the aesthetics. And his focus will be on the aesthetics, whereas the engineer will look at the practicality, the calculations, and what can stand and what can't stand, and how to. Maybe the engineer will. Best way to explain it is the engineer will try to put into practice the vision of the architect, what he wants to see, because he is often employed to make something look fantastic, to make something become a kind of icon or a symbol of a country or a town, whereas the engineer is just like, well, will it work? And how can we put that vision into practice?
So basically, the engineer is the unsung hero of the. You talked about this being a teamwork, right?
Yeah.
This whole building business.
I think it can often, especially in big iconic projects, it can often be attributed solely to one person, and that's unfair.
But they do that, though. I mean, I know this from
like
Sydney Harbour.
I think it's a human thing to attribute everything to kind of one hero, and we want our heroes.
It's easy.
Yeah,
it's simple.
I mean, the first man on the moon.
Yes.
Right,
yes.
Neil Armstrong. But what about the second man?
Buzz Aldrin.
And what about the guy who piloted? He didn't get to step on the moon, but without him,
that's right.
Michael Collins.
Would have never got there.
Michael Collins. I mean,
I've never even heard of the guy until you told it to me.
Right.
Yeah. So I didn't even know he existed.
It's a kind of, to be honest, it's a kind of generic name because
there's another. It is a very. Isn't there an Irish Michael Collins?
There is a history, a more historic figure, Michael Collins.
Now, like for example, like Sydney Opera House, an icon of Sydney. Everybody remembers the architect behind that,
right?
But nobody ever says anything about the engineer.
And it was a team. It wasn't just one architect.
Right.
It was a team.
That's right. And and what are some of your favorite structures?
Well, so I talk about style. is I like, as far as architecture, I like older styles. I'm not a fan of a lot of glazed, a lot of windows. I'm not a fan of it. And I think that it can look good, but I think it can heat a building too much as well. I like Victorian architecture, coming from the UK maybe, but it's quite popular actually in many of the cities, and I like it. Right. This older style, and I also like Gothic too. And it's maybe it's a personal thing, of course, but I like these old gargoyles and things. I'm a lover of Batman, you might have guessed. Okay, yeah. And Gothic is, of course, connected with that, and maybe it's just a whole holistic thing. But I like the use of stone. And I love the use of arches. I think not only is the arch practical, but it is beautiful.
And what are the materials used for these sort of?
Right. So to talk about the materials, we mentioned the forces about pressing forces, compression, and bending forces, tension. And these are the two main forces that you should consider. There are others too, of course, but one material that's quite good that adapts to those needs is reinforced concrete. Okay. And those who don't maybe know much about bridges and construction will not realize that it's not just one lump of concrete. Your walls are not just concrete, which is your cement and your stone, right? It's not just that water plus the cement plus your paste, your cement paste and the stone thrown in. It often, especially if it's a serious building, even if it's a wall, it will have steel inside. Yes. These steel rods. Yes. And it's often called rebar or it's reinforced steel. And these are of different shape, different diameters. And they're calculated very carefully based on what is pressing down or pushing that structure. The steel is very good in bending. It's very good in the tension. Yes. So those rods are there to stop it from bending and break, and in the end it will break. The concrete is excellent in pushing in the compression. So those two complement each other. They work together like kind of a friend.
That makes sense, because I always thought that they put the steel beams inside concrete, because I thought originally because the half-life, so the degradation rate of the concrete was approximately the same as steel inside. But that's not the case. They say they're complementing different types of forces.
It's different forces.
I see.
And it can, back to the water, if the water gets in, it can rust that reinforcement, unfortunately. Then it can start to break the concrete. So while they complement each other, they can also work against each other.
I see. So this is why maintenance is so necessary.
Inspection. Yeah. So you've got reinforced concrete, you've got steel, pure steel just, and iron we mentioned. You can have a combination of those. You can put wood, you can use wood, but not for too many, not for serious. Stone can also be used too. But you've got all of those different things, and there are benefits to each of them.
I see.
So that was the crack about construction.
Oh, thank you very much.
Did you like that?
I think I learned a lot about construction.
Great. So we talked about what kind of what is construction and who is involved. It's a team. It's not just one person. We talked about the different types of structures you might meet as you walk down the street without even thinking of it, without even being conscious. We spoke a little bit about different types of structures that there are in the world, the forces that act on them, some problems, we mentioned those, materials as well, and who is better, or what's the difference between an architect and an engineer, and a little bit about favorite style, just a little bit. So guys, girls, that was the crack about construction.